Algebra 1, Lesson 5-2, Direct Variation. Learning target. I will be able to write and graph an equation of direct variation. Warm-up. The diagram shows how long it takes to hear thunder after you see lightning. What general rule can you use to model this situation? Explain. Since the time it takes for you to hear the thunder after you see the lightning varies directly with the distance you are from the lightning strike. Speaking of weather, they say red sky at night, sailor's delight, red sky at dawn, whatever they say. Well, blue sky at night, they call it day. Terminology. Direct variation. A relationship that can be modeled by a function in the form y equals kx, where k cannot equal 0. Constant variation for direct variation. K is the coefficient of x. To determine whether an equation represents a direct variation, solve for y. Example 1. Identifying a direct variation. Which equation represents a direct variation model? For the direct variation model, find the constant of variation. So in the first case, we solve for y. So we divide both sides by 8, and we end up with y equals 3/8 x. Notice this is in the form y equals kx, where k equals 3/8. For b, we also will solve for y. So the first thing I'll do is I will take 4x away from both sides, and I end up with negative 3y equals negative 4x plus 9. Then I divide both sides of the equation by negative 3. And I end up with y equals negative over negative is a positive 4/3 x minus 3. However, it should be noted that the negative 3 means it's not direct variation. Since y equals mx plus b. This is direct variation. Example 2. Writing a direct variation equation. Suppose y varies directly with x, and y equals 22 when x equals 7. What is the direct variation equation that relates x and y? What is the value of y when x equals 2? So the first thing is, we are told that this is direct variation. Since we know it's direct variation, we know we're going to have a model that is y equals kx. We also know that when y equals 22, x equals 7. So I'm going to substitute those values into the direct variation equation and find out what k is. So y is 22 when x is 7. If I divide both sides by 7, I end up with 22/7 equals k. So that is the constant of variation. can use that constant now to create the direct variation model of y equals 22/7 times x. So when I want to know what the value of y is when x is 2, I will substitute the 2 into the model. 2 times 22/7 is 44/7. And that is my answer. Graphing a direct variation model. Example 3. So space exploration. Weight on Mars, y, varies directly with the weight on Earth, x. The weights of the science instruments on board the Phoenix Mars lander on Earth and Mars are about to be written. So on Earth, the weight of the Mars lander is 130 pounds. On Mars, the weight of the Mars lander is 50 pounds. We're told that the Mars weight is y and the Earth weight is x, and that it varies directly. So we know that we have a direct variation equation. To find out what our constant of variation is so that we actually have the correct equation, we will substitute the 130 pounds in for x and the 50 pounds in for y and solve for k. So substituting 50 pounds in for y and 130 pounds in for x and solving for k, we get k is 5/13. This gives us the equation. Another way to write that would be the decimal form, which is y equals 0.38x. Next we'll make a table based on that. So putting the Earth weights 0, 50 pounds, 100 pounds, and 150 pounds into a table and using the formula to convert to Martian weight, we see that 0 pounds on Earth is 0 pounds on Mars, 50 pounds on Earth is 19 pounds on Mars, 100 pounds on Earth is twice the Martian weight, which is 38 pounds, and 150 pounds on Earth is 57 pounds on Mars. So we'll use that data to then construct or sketch a graph. So we see that for the horizontal scale, we're in weight on Earth, and for the vertical scale, we have weight on Mars. So we place our 4 ordered pairs or coordinates in the xy plane, and I actually connect them with a line because you can have any weight, so it's a continuous graph rather than a discrete graph. So just as a concept summary, graphs of direct variation. The graph of direct variation equals y equals kx, where k is the constant of variation, and that's a line that passes through the origin 0, 0 and has the slope k. When k is greater than 0, as we go from left to right on the graph, the line goes up, and if k is less than 0, that is it's negative, then as we go from left to right, the graph goes down. So we can say up with a positive coefficient of variation and down with a negative coefficient of variation. One other thing I'd like to say is about the constant k and the ratio of y over x. Notice that since y equals kx, if I divide both sides by x, what I end up with is y over x equals a constant. So what this tells us is the ratio of y over x is always the same. And that'll be important for certain cases. Speaking of that being important, let's take a look at example 4. Write a direct variation model from a table. For the data in the table, does y vary directly with x? If it does, write an equation for the direct variation. Now the thing is, we'll know it's direct variation if the ratio is constant for each ordered pair. So for instance, I have the ordered pair given here. So the question is, why? We know that y over x should be constant. So 6 over 4, which by the way is the same as 3 over 2 or 1.5, should be the same as the next case, which is 12 over 8, and 12 over 8 is the same as 6 over 4, which is the same as 3 over 2, which is 1.5. And finally, we have 15 over 10 for y over x, and 15 divided by 10 is 1.5. So we can see that all of the ratios are constant, so we know that this is direct variation. So again, ratios constant means direct variation. And so that was part A. Looking at part B and checking the ratio there, I have y is 3 over 2 divided by x, which is negative 2, and that equals negative 1.6. For the second ordered pair, I have 2.4 divided by 1, which equals 2.4. So actually I can stop right there. These guys don't equal each other. The ratios are not the same, so not direct variation.